For the second part of our intro to acids, I want to talk about calculations because that's what you guys are working on for your pre and post lab. So from this video, I want you guys to be able to calculate the pH of a solution of an acid or a base. I want you then to be able to determine the number of moles of an analyte and titrant that are being added during an acid-base titration. I want you to be able to calculate the pH of a reaction after it's been completed, and then to visually represent the changes, what changes and what stays the same during a dilution. So to talk about this, we really need to talk about the relationship between H plus and OH minus. In the first part of this video, I talked about that water does dissociate to a very, very small extent into H pluses and OH minuses. If you notice, that's 10 to the negative 7th molar. That's a really, really small concentration of each, but it's significant, and that's what we use to determine the pH of a solution. So when water itself breaks apart, one water generates one H plus and one OH minus. So our definition of a neutral solution is when only water is splitting apart to generate those two, so they're both going to be the same relative amounts. If I was to draw that out, I would say H2O, H plus OH minus, that when any one water breaks apart, it only generates one of each of these, so that means that they would have to be equal in concentration. That's why when these two are equal to each other, that is considered neutral. Okay, so now that we got that down, and that both of those, this is our definition, when both of those are equal, then that gives us 10 to the negative 7th molar concentration of each one. Okay, so let's talk about pH. So pH, because concentration of H plus ranges over such a large number, we can have 1 molar H plus, or we can have 1 times 10 to the negative 10th molar H plus. That's a really big difference. So what we've done is we made a logarithmic scale. So if we do the negative log, basically what we're telling you is, well, what is the exponent? What order of magnitude is the H plus concentration? Here, it's an exponent of 1. Here, it's an exponent of negative 10. So let's do some calculations with that in a minute. So if we're at neutral pH, the pH of that solution is negative log of the concentration of H plus that's in a neutral solution. So negative log of 1 times 10 to the negative 7th. Taking the negative log means that the exponent falls off the log, and the negative means it changes sign. So that means we have a pH of 7, that is a neutral pH. Let's do the same thing for pOH then. pOH, that P means we're going to take the negative log of whatever's next to it, OH in this case. Just like we did up here, P means negative log of H. We're being kind of sloppy. It really should be H plus, right? But in chemistry, we don't do that. It's kind of a shorthand. So pOH minus means the negative log of the concentration of OH minus. So then what's the pOH of a solution of neutral water that has 1 times 10 to the negative 7th molar of OH minus? We would find that by taking the negative log of 1 times 10 to the negative 7th molar to find the pOH, which in this case is also 7. What do you notice about the sum of pH and pOH for a neutral solution? I'm hoping that you guys see that pH plus pOH always adds up to 7. And it turns out that this holds true no matter what, because as H plus concentration goes up, OH minus concentration goes down, but they always will multiply together. H plus concentration times OH minus concentration always equals 1 times 10 to the negative 14th. That means that this one goes up, then the other one will have to go down. So let's keep this in mind. If we know pOH, we can find pH. If we know pH, we can find pOH through that relationship. So go ahead and try this problem. So we want to calculate the pH of rainwater collected in a certain region of the northeast US on a particular day, and that was 4.82. Question is, what is the H plus ion concentration in the rainwater? Go ahead and pause and try to work through this. First thing we need to do is to go ahead and write out what's the relationship between pH and concentration of H plus. In this case, we know what the pH was. and we're trying to find the concentration of H+. And the way that we can undo the logs is we multiply both sides first by a negative value, so we multiply by -1, and then we take 10 to the both sides, and that gets rid of log. So that means the pH of this solution was 10 to the -4.82 molar, and I think I have these all written out, which would be 1.5 times 10 to the -5th molar. What about OH minus ion concentration then? Pause for a second and see if you can find what the pH of the solution was if we know the OH minus concentration. So here we need to use our other definition of POH equals negative log of OH minus. We know the concentration of OH minus, so we should be able to find the POH. But it's not asking for the POH, it's asking for the pH. So let's use this relationship to find the pH. If we find our POH, we can find that that is 6.60, and then from that we have to find the pH, so we do 14 minus the POH to find the pH. So this is a slightly basic solution, and if you're noticing trends, we notice that this is slightly higher concentration of OH minus than we have in a neutral solution, meaning the solution is a little bit more basic than neutral, and the higher the pH, the more basic it is. Now let's do a little bit more of a complicated problem like you guys had in your pre-lab material. Go ahead and take a minute and pause, see if you can start this problem. If we have 132 milliliters of a 0.578 molar sodium hydroxide solution, what is the initial pH? So the first thing that we should do is we should write out an equation where we have NaOH added to water, and we know that when we do that, we have an ionic bond that will separate between a polyatomic ion of hydroxide and a sodium cation, and the water just sits there. It was what allows this to happen. So that means that however many sodium hydroxides we have is the same as the number of hydroxides we have. So let's go ahead then and say if we have 132 milliliters of NaOH solution as our starting quantity, what do we do in order to find the number of moles? Luckily we have a conversion factor that allows us to go from moles to liters, so once again I'm going to write this out and make sure to expand all the units that are hidden in molarity. So we know that we have 0.578 moles of sodium hydroxide for every 1 liter of sodium hydroxide solution. What that allows us to do is convert from liters of sodium hydroxide solution to moles of sodium hydroxide. And one thing that you might have noticed is I actually didn't even touch the milli. So let's leave that for now. So what we find, if we then calculate 132 times 0.578, is we find 76.296. I didn't get rid of the milli though, so I have to leave that. And then we have moles of NaOH. What we find when we left that milli was that this milli stays put, meaning it's really 76.296 times 10 to the -3rd moles of NaOH. I actually prefer to use millimoles instead of times 10 to the -3rd moles because it gives me a better idea of how big that is. Okay, so now we know how many moles of sodium hydroxide we have in that initial solution, and I'm just going to write this down on a separate piece of paper so I don't lose it. So we have 76.296 millimoles of NaOH. Alright. And then we added HCl to it. So here's a balanced equation where we added hydrochloric acid, and you guys should be able to predict what products we form from this reaction and others. So then I want to know what the initial pH of that solution was. So let's pause. So it looks like I actually answered the second question before the first one. So let's go ahead and find the pH of that first solution. Does the amount of it matter to find the pH? I hope you're saying no, it doesn't. All we need is the concentration. So we know that POH is always equal to negative log of the concentration of OH minus. And since with the first equation that we wrote out, we said that the concentration of NaOH is actually the same as the concentration of OH minus, because every one NaOH separates into one OH minus. So that means that we can find the POH by taking the negative log of 0.578 molar. And if we do that, negative log of 0.578, then we find that the POH equals 0.238. But it's not asking for pH. So how do we find the pH? To find the pH, we need to do 14 minus POH, and that is a very high number, 13.761. Because we're using logarithms, that means that only the number past the decimal is significant. So this is 3 sig figs. That means that we go 3 past the decimal. We'll talk more about this in class. Okay, so now we know how many moles of sodium hydroxide, 76.296 millimoles of sodium hydroxide were there. And then the next question is, we then add some HCl, 15.5 milliliters of a 0.200 molar HCl solution to the sodium hydroxide. How many moles of HCl were added? Let's go ahead and pause and try to calculate how many moles of HCl we added. I'm hoping with this, you're automatically saying, well, we know what the initial quantity of HCl was, and we know what the concentration was. For every 1 liter of HCl solution, we have 0.200 moles of HCl. That means that we added 3.10 millimoles of HCl. Once again, you might have noticed that I canceled out liters of HCl solution, but not the milli. That means that we left moles of HCl, but we have a milli in front of it, which is why I have millimoles on the right side of the equation. Okay? So we had 3.10 millimoles of HCl. So the next question is, how many moles of HCl or NaOH are left after the reaction goes to completion? So let's write out how much of each one we have. We know that we had 76.296 millimoles of NaOH and 3.10 millimoles of HCl. So the question is, well, how do they react with each other? If we go up to the top, we can see that if we balance this equation, it is already balanced. So we need 1 mole of NaOH to react with 1 mole of HCl to form 1 mole of water and 1 mole of NaCl. So that means the one that runs out first is going to be the one that has less moles, because it's a 1-to-1 stoichiometric ratio. Let's write that out. So if we have 3.10 millimoles of HCl, we know that it reacts 1 mole of HCl for every 1 mole of NaOH, and that means that we need to use 3.10 millimoles of NaOH used. So then how many are left over? If we used 3.10, but we had 76, we need to find the difference. So we started with 76.296 millimoles. We used up 3.10 millimoles. So that means that we have 76.296 minus 3.10 means that we have 73.196 millimoles NaOH left. Great. The last question we're going to have to answer then is, what is the pH of the solution? In order to find that, we have to use the number of moles and the volume in order to find the pH. So let's write out molarity equals moles of solute over liters of solution. Well, we know that the one that we have excess of, the only one that's left over, we used up all the HCl. So we know we have 73.196 millimoles of NaOH in a volume of, we started out with 132 mils, we added 15.5, so we have a total of 147.5 milliliters of solution. The nice thing to notice here is we don't actually have to convert from milli to non-milli, because we have a milli on the top and a milli on the bottom. So let's find out what that numeric value of that ratio is. When I find that ratio, I find it is 0.496 molar NaOH. How do I find the pH then? Well, let's go through the steps we did before. Let's find the pOH, which is negative log of the concentration of OH minus, which is the concentration of NaOH. So negative log of that answer is 0.304, and then we do 14 minus that answer in order to find that the pH is 13.696. That is how we find the pH of a solution after it has had some neutralization occur. Neutralization is when a strong acid and a base combine. Now I want you to take a minute, pause with this problem. Now the challenge is, make sure you balance this equation properly and see what's different between this reaction and the last reaction. Once you balance this equation, I hope that you noticed that you actually need to have 2 sodium hydroxides to react with 1 sulfuric acid to use up all of the acidic protons, because there are 2 acidic protons. That gives us 2 waters and 1 sodium sulfate. So now go ahead with this balanced equation and try to go through the steps we just did to determine what the pH of the final solution will be. The first step we're going to do is answer how many moles of sodium hydroxide were added during this titration. Just like we did before, we would want to take the initial volume of our analyte, the one that we're analyzing. We ended up having a 1.42 molar solution. So once again, we'll write out that conversion factor in full, that we have 1.420 moles of sodium hydroxide in every 1 liter. We don't have a liter though, we have less than that, we have 0.158 liters. So that will tell us the number of moles of sodium hydroxide that we had there in the first place, we added to the initial solution. The next question then is, how many moles of sulfuric acid were present in the analyte? In order to figure out how many moles were present, we can either start with the number of moles of sodium hydroxide that we had. Maybe we should be a little bit more specific before we go on with these calculations. The question is asking, and maybe if we draw it out, this always helps. We have a analyte. We have a solution here, and in that solution we had 25.00 milliliters of H2SO4. We don't know what the concentration is. We do know that if we added sodium hydroxide, which took 158 milliliters, and we know that we had to add that was a 1.420 molar solution of sodium hydroxide. That however many moles were added here, that these were enough to use up all of the moles of H2SO4. Since we know that this is moles of H2SO4 per liters of H2SO4, that's our definition of molarity, we know that we have 0.02500 liters. So the only thing that we don't know is how many moles of sodium hydroxide or sulfuric acid were there. However, if we could figure out how many moles we added, we would know that we used up all of the sulfuric acid in the process, so the number of moles would be relative to those. So now let's go ahead and try to see. We know that we added 0.112 moles of sodium hydroxide. Is that the same as the moles? So that is our moles there. The question is, how does that relate to the number of moles of sulfuric acid that were there? To go back to our balanced equation, we know that we need 2 moles of sulfuric acid for every 1 mole of 2 moles of sodium hydroxide for every 1 mole of sulfuric acid. So let's see how this all works out. So once again, if we started with how much sodium hydroxide we added, we know what the concentration of it was. We now would have found the number of moles of sodium hydroxide added to get to the point where there's no more of the sulfuric acid. Another way to say this is that up until this point, sodium hydroxide was a limiting reagent, and now it's not. But we want to know how many moles of sulfuric acid were there. So we can use a molar ratio to determine how many moles of sodium hydroxide there were to consume all of the sulfuric. Let's say that in a clear sentence again. That by adding 0.158 liters of sodium hydroxide solution, we are now determining the number of moles of sulfuric acid that were present, because we know that 2 moles of sodium hydroxide react with 1 mole of sulfuric acid. So this tells us that in this solution, we need to do some math because those numbers are the same. And what we find is that I made a careless mistake up above, and that this is 0.224 moles of NaOH. So the bottom calculation is accurate. I just carried over some bad PowerPoint material above. So what we find is that the amount of sodium hydroxide added is twice the amount of sulfuric acid that would have been there. We can predict that based on the balanced equation. So then the last question is, or could be, what was the original concentration of the sulfuric acid solution? And we know the concentration, as we were showing before, was the number of moles in the number of liters. It's always that ratio. When we're given molarity, it's always per 1 liter, but to find it, we can do whatever the ratio is. So if we know how many moles of sulfuric acid and what the volume of sulfuric acid was, we can very easily find the molarity of that solution. The last part of this is that if you want to do any sort of dilutions, we need to think about what the concept is that's happening in dilution. So I want you to go ahead and answer this question. If we add water to a solution, what happens to the number of moles of the solute that were in that solution? Go ahead and click in your answer, aka write it down. If we take a look at this, the red dots show the solute in a solution. If we add water, the only thing that's going to increase is the amount of water. Hopefully you can tell we're not going to change the number of particles that are in there. So for instance, if we have sugar water and we add water, more water to it, the only thing we're going to add is water. We're not adding or taking away sugar. So there's a much larger volume now that they occupy. The second question is, if we added water to the solution, what happens to the concentration? And remember, concentration is always the ratio of solute to solution. In this case here, we have a much greater ratio because we have the same amount of solute. So let's say we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 solutes per, let's just say that this is 100 milliliters. On the right side, the number of particles didn't change, so we still have 18. But now we have about twice as much volume. So that ratio is lower, meaning that the concentration of the solution decreases when we add more water.